Okay, hydrostatic pressure and force. Deep sea divers realize that water pressure increases as they dive deeper. This is because the weight of the water above them increases. In general, suppose that a thin horizontal plate with area square meters is submerged in a fluid of density, this is called rho, kilograms per cubic meter at a depth d meters below the surface of the fluid, as you can see in figure 5. The fluid directly above the plate has a volume V, which is equal to A times D. So its mass is M, which is equal to rho times the volume, which is equal to rho times A times D. Now the force exerted by the fluid on the plate is therefore the following. The force, which is equal to mg, which then becomes rho times g times A times D, where g is the acceleration due to gravity. Now the pressure P on the plate is defined to be the force per unit area. P, which is equal to the force over the area, is equal to rho times g times D. Now the SI unit for measuring pressure is newtons per square meter, which is called a Pascal. An abbreviation is 1 Newton per meter squared is equal to 1 Pascal. Since this is a small unit, the kilopascal is often used. So for instance, because the density of water is rho, which is equal to 1,000 kilograms per cubic meters, the pressure at the bottom of a swimming pool 2 meters deep is the following. So here's our pressure. We're going to take 1,000 kilograms per cubic meters times 9.8 meters per second squared, the gravity, times 2 meters. We would then get 19,600 Pascal, which then converted to kilopascal, which becomes 19.6. Now again over here, when using US customary units, we're going to write the following. Okay, you're going to see that the pressure is equal to rho times G times D, and then we end up getting a weight density. So for instance, the weight density of water would then be 6.25 pounds per cubic feet. Now, an important principle of fluid pressure is the experimentally verified fact that at any point in a liquid, the pressure is the same in all directions. So a diver feels the same pressure on nose and both ears. Thus, the pressure in any direction at depth d in a fluid with a mass density rho is given by the following. So here is our equation number 5. And this helps us determine the hydrostatic force against a vertical plate or wall or dam in a fluid. This is not a straightforward problem because the pressure is not constant, but increases as the depth increases.